Hello, everyone. My name is Gideon Koech from Vaal University of Technology, South Africa. My promoter is Dr. Jean Vincent Panu, and I'm going to present a paper on K-nearest neighbors classification of semantic web ontologies. The semantic web is basically an extension of the current web, and ontologies are the basic building blocks of the semantic web. Over the recent years, we've seen growth in of the semantic web, and with this growth, there has been an increased number of ontologies. The process of selecting an ontology to be used by ontology developers and ontology users can be tedious and time-consuming, and this has been a problem. Ontology reuse has come into play, and it entails the use of existing ontologies in building new ones. Over the recent past, the process of selecting ontologies has only been limited to keyword search and also the use of ontology libraries. A candidate ontology can also be selected using a number of metrics, and these metrics can measure the quality of an ontology. Some of these metrics are accuracy, computational efficiency, understandability, conciseness, and cohesion. In this paper, K-nearest neighbors algorithm, which is a machine learning algorithm, has been used to classify ontologies by basing on their quality metrics. The main aim is therefore to group these ontologies that display the same quality properties into classes, thereby providing some insights for ontology users and ontology developers into the selection and the reuse of these ontologies by the use of machine learning techniques. Some of the related work on ontology classification has only been on the task of computing the subsumption hierarchies for classes and properties in recent systems to measure the satisfiability and consistency of ontologies. Also, the term ontology classification in a semantic web ontology field has only been used in the classification of proteins. And we've only seen that this has only been manual classification of ontologies. A study has also been carried out where a review of existing ontologies was performed, and a manual classification of these ontologies according to the engineering phase that they are related to and the type of information that they model, and also the scope of their application. Machine learning algorithms has also been implemented in ontology alignments based on the changes that may occur in an ontology over time. K-nearest neighbors algorithm, as we all know, it's a machine learning algorithm, has also been applied for loan forecasting, classification of heart diseases, and also in data mining for the classification of medical literature and many more. Material methods and quality metrics of an ontology. So the quality metrics of an ontology considered in this study are adopted from ontometrics, which is a state-of-the-art tool for automated ontology evaluation. 11 quality metrics under the schema, knowledge base, and graph categories of ontometrics has been used as attributes in the dataset that was used in building the K-nearest neighbors classification, K-nearest neighbors algorithm in performing the classification of these ontologies. The schema metrics selected include the attribute richness, inheritance richness, and relationship richness. The knowledge base metrics category encompasses the average population and class richness, the absolute root cardinality, absolute leaf cardinality, average depth and maximum depth, also average breadth and maximum breadth, form the graph matrix in the ontometrics tool. Now, the above quality metrics in ontometrics tool correlates with the quality and evaluation criteria or the quality dimensions of ontologies. And these quality dimensions include accuracy, which indicates the extent to which an ontology can evaluate under evaluation represents the real world domain in its modeling. Another quality dimension is understandability, which evaluates the comprehension of the constituents of ontologies, such as the concepts, relationships, properties, and their meanings. Cohesion is another quality dimension, which indicates the degree of relatedness amongst the constituents of the ontologies. Conciseness is another quality dimension, which measures the degree of usefulness of the knowledge in an ontology. K-nearest neighbors algorithm. This algorithm can be used for classification, estimation, or prediction, and is an example of instance-based learning. The algorithm works by first loading all the data points that are in a dataset in its memory. The algorithm then makes a plotting of the data in an n-dimensional space, which means it can use any space, and this can change, or it depends on the type of data that is being used or the data that is being fed to the algorithm. Each and every point on the plotting area represents a label in the dataset. A test sample, which represents a set of training data, shall also be plotted within the same n-dimensional space. It will then make a search for its k-nearest neighbors on the basis of a specific distance measure out of the training samples. Some of the performance measures that has been used in checking the performance of this algorithm includes accuracy, precision, and recall, F measure, and also receiver operating curves. On the experiments conducted, the dataset was first split into the training and the testing sets using a ratio of 0.3. The different values of K, nearest neighbors, were used to find one with the best accuracy score. In this case, what the experiments that was conducted, different values of K were tested to check the one that had the highest accuracy score. And for this case, we found out that for the value of K as 5, the model displayed an accuracy of 67% and an average precision, recall, and F measure scores of 69%, 67%, and 67% respectively, as shown in figure 1 here. So the support column in figure 1 shows the total number of ontologies that were classified per class. And in this case, we can see there are 4 classes, and these 4 classes represents the 4 quality dimensions that was introduced earlier. So we used the number 0, 1, 2, and 3 to represent the 4 quality dimensions in that order. And we can see, for example, the first class, with which is shown by 0, had a total number of 14 ontologies that were classified into that class. So these numbers of classes are confirmed in each row of the confusion matrix on the figure 2 shown. Okay. The actual values of the class labels 0, 1, 2, and 3 that were predicted correctly are 10, 10, 6, and 14, as shown. And these figures, the values on the other cells were misclassified by the model. Two sets of receiver operating curves were generated, including the macro average curve for the 4 class labels and the receiver operating curves for the individual class labels. These curves are as shown in figure 3 and figure 4. So we can see in figure 3, there's the macro average for the 4 onto the 4 quality dimensions, or the 4 classes for that matter. And on figure 4, we can see the 4 different rock curve for each and every class, including a macro average for the 4 classes. So the receiver operating curves evaluate a model by checking the area under the curve. And as shown in figure 3, in figures 3 and 4, the macro average for all the classes is 0.78. The area under the curve for the class labels 0.0, 1, 2, and 3 are 0.78, 0.68, 0.69, and 0.96, respectively, in figure 4. These curves evaluate the scores in the range of 0 to 1, and the scores obtained in figures 3 and 4 indicate that the model is a good classifier because the value is close to the value of 1. Conclusion. The performance of the model was evaluated using the metrics that were discussed, which include precision and recall, F-measure, and also receiver operating curves. So the overall accuracy for this model was 67% for 5 values of K. And this showed that this particular algorithm is a good classifier for semantic web ontologies. So the future direction of this research would be to implement more learning algorithms to classify more ontologies and to compare their performance. Another direction can also be to increase the dataset, because we only use a total number of 200 ontologies, and more ontologies can be obtained from ontology libraries, and they can be classified according to any given criteria. These are the references that I used. And thank you for listening to my presentation.